To truly understand how magnetic fields behave, we often turn to powerful tools like Ampere's law. But before we can use it to calculate those invisible forces, there is a crucial first step we must master. It is figuring out which currents actually contribute to the magnetic field we are measuring. So, when is current truly considered enclosed for Ampere's law? A current is considered enclosed for Ampere's law when it passes through any arbitrary open surface that is bounded by your chosen Amperian loop. Simply put, if you can imagine stretching a membrane or a soap film across your closed Amperian path, any current that pierces that membrane is counted as enclosed. The fundamental principle here lies in the topological nature of Ampere's law. The law states that the line integral of the magnetic field around a closed loop is directly proportional to the total current passing through the surface enclosed by that loop. Crucially, this surface is not unique. You could choose many different surfaces that all share the same boundary, which is your Amperian loop. However, all these surfaces must enclose the exact same net current. This consistency is a direct consequence of current conservation. If a current source starts inside the loop and passes through one surface, it must also pass through any other surface bounded by that same loop to leave the volume defined by the loop. This ensures that the total enclosed current, also known as I enclosed, remains constant regardless of the specific shape of the surface you choose, as long as its perimeter is the Amperian loop. To practically identify the enclosed current, first clearly define your Amperian loop. This is an imaginary closed path in space where you will perform your line integral. Next, visualize any arbitrary open surface that has this loop as its boundary. Imagine it like a net or a thin sheet. Then, identify all currents that pass through this imaginary surface. Currents that run parallel to the surface, or those that are entirely outside the loop, are not considered enclosed and do not contribute to the I enclosed term. Remember to apply the right-hand rule to determine the positive direction of the current relative to the direction of your Amperian loop. If your thumb points in the direction of the current and your fingers curl in the direction of the loop, that current is considered positive. This powerful concept allows us to vastly simplify calculations for systems with high symmetry, such as long straight wires, coaxial cables, or toroids. Instead of performing complex volume integrals, we can identify a simpler, more convenient surface for the current. The beauty is that even if the actual physical surface enclosing the current is complicated, the mathematical surface you define for Ampere's law can be chosen to be flat or cylindrical, making the calculation much more manageable. This freedom in choosing the surface is a cornerstone for applying Ampere's law effectively to derive magnetic fields. Grasping the definition of enclosed current is not just a theoretical nicety. It is the practical key to unlocking Ampere's law for magnetic field calculations. By understanding that any current piercing your chosen surface contributes to the magnetic field, you gain the ability to choose the most advantageous Amperian path. This allows you to apply this fundamental electromagnetic principle with confidence, leading to accurate solutions for a wide range of engineering problems involving magnetic phenomena.